The final topic in our prerequisites chapter is dealing with all sorts of different square roots and generally simplifying and evaluating any type of fraction or square root, radical, or complex fractions, rationalizing, things like that. So the last section that we need to do is 1.3, simplifying and evaluating. So for example 1 and example 2 that we're going to cover in this video, those deal with anything with radicals, okay? And radicals are just square roots, which hopefully someone has taught you at some point how to simplify those square roots. I like to use what's called a birthday cake method. You can also think about taking out perfect square factors, so pulling out things like 4, 9, 16, 25, things that are perfect squares. So I'll talk about both of those as we go. So in example A, example 1 wants us to simplify the following radical expressions. Well, radical expression just is an expression with a square root, or a third root, or a fourth root, or something like that, by combining the radicals, okay? You can only combine radicals, so only can be combined if the number under the radical matches the number under the other radical, okay? So like if you're looking at letter A, where it says the square root of 32 plus the square root of 200, you can't just put those together and say, oh, that's the square root of 232. You can't add radicals like that. You can only add them if they're exactly the same. So to do that, we need to simplify them to where they're down to their smallest possible bits, and then see if those things can combine. So if you're looking at the square root of 32, you might know the birthday cake method. That's kind of my favorite. It's the easiest to use, but I also think for these purposes that you need to make sure that you're used to pulling out perfect squares. So if I'm looking at 32, I'm trying to think of a number that's a perfect square that goes into 32. Well, numbers that are perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, and I'm going to stop there. You could continue the list, but it's things like that. So things that like 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. So perfect squares that you could pull out. So this is kind of what I'm doing in my head. I'm looking at the 32 and I'm going, okay, well I know that 16 goes into 32. So I know I could break this square root into the square root of 16 times the square root of 2, because 16 times 2 is 32. I could also break the 200 down into the square root of 100 is a perfect square, and that would be 100 times the square root of 2, right? Well, the square root of 16 is 4, so this piece is 4 square roots of 2, okay? The square root of 100 is 10, so this piece is 10 square roots of 2. So now do you see that both of the square roots are the same? So we can add the coefficients. So this is the square root of 2, this is the square root of 2. I have 4 of them. I have 10 of them, so I really have 14 square roots of 2. So once you get square roots down to where they match, where they're the same radical, they work just like exponents, or sorry, just like variables do. You've got to have like terms so that you can put them together, okay? Take a look at B. B is a fifth root. So in order to pull things out that are fifth roots, you need to have, this side we had perfect squares because they were square roots, so 1, 4, and all of those things. This side, you have to have perfect fifths, okay? And perfect fifths, the ones you probably need to know are 1, and then 2 to the 5th is 32. 3 to the 5th is 243. And anything past that that you memorize is totally fine. It's just kind of remembering what you can remember, okay? But really the big one that you need to know are these two. 32 is one you're going to need to recognize as 2 to the 5th, okay? So make sure you're recognizing that. So looking at this guy, I know that 32 times 3 is 96. So I know this is the 5th root of 32 times the 5th root of 3 plus the 5th root of 3, because that one doesn't reduce. The 5th root of 32 is 2. So this is 2 5th roots of 3 plus the 5th root of 3. So I have 2 of them. I have 1 of them. So I have 3 of them. So 3 5th roots of 3. And if pulling out the roots that you know that are perfect fifths or perfect squares or whatever, if that doesn't work for you, I always use the birthday cake. So I would have taken the 96. So let me show you how that works. I would have taken the 96 and divided it by the smallest thing that I know that goes into 96, which is 2. And 2 goes into 96. 2 goes in there, 4 times with 1 left over, so 48 times. The smallest thing that I know that goes into 48 is 2. That's 24. The smallest thing is 2 again. That's 12. 2 again. That's 6. 2 again. That's 3. And 3 leaves me with 1. So that's why they call this the upside down birthday cake method, because you always get to the bottom where there's a 1. And if you kind of look at it, you could make a candle and there's like some smoke, right? So it's an upside down birthday cake. So when you get to the candle, you know you're at the end. But we're looking for groups of 5 because this is the 5th root. So 1, 2, 3, 4, 5. So I've got 5 2s. This number goes in the front. So this is 2 5th roots of the remainder, which is 3. So this would be 2 5th roots of 3. So either one of those two methods, pulling out the perfect squares or perfect fifths, or birthday caking, whatever, just make sure you figure out which way works for you and know a way to simplify radicals, okay? The other thing that we need to do with square roots is rationalize, okay? You're gonna need to know how to rationalize for any number of reasons. There's lots of reasons we need to know how to rationalize. Sometimes to find limits when in Cal, sometimes to simplify answers to just make them a little bit easier. But in order to simplify, when we're talking about rationalizing, you're talking about no radicals being left in the denominator. Okay, so you can't have any radicals left in the denominator. And that rule kind of gets a little hazy in Cal because sometimes we're going to leave them, sometimes we're not. But in general, it is a skill that you need to know how to do. So looking at A, we cannot leave a radical in the denominator. So what we do is we multiply the top and the bottom by whatever radical you have on the bottom. So I'm going to multiply the top and the bottom by the square root of 3. Because technically, the square root of 3 over the square root of 3 is just a fancy form of 1. Right? It's a fancy form of 1 because it's the same number over itself. So it's not going to change the value of this expression. It's just going to manipulate it to where we want it to be. So if I multiply the top by this, I get 2 square roots of 3. And if I multiply the bottom, I have the square root of 3 times the square root of 3, which is the square root of 9, which is 3. So this is equivalent to this. It's just the rationalized form because there's no square root on the bottom, okay? This guy right here, we can't rationalize it because you've got to have the square root in the denominator, right? But the square root of 12 does simplify. So the square root of 12, if you think about perfect squares, because it's a square root, I know that 4 goes into 12. So this is the square root of 4 times the square root of 3 over 4, because 4 times 3 gives me 12. The square root of 4 is 2. So this is 2 square roots of 3 over 4. And 2 over 4 simplifies to 1/2. So this is the square root of 3 over 2. It simplifies down, okay? This guy looks a little bit different. Normally what I'm gonna do whenever I have weird roots with powers, remember in one of the last videos we talked about the fact that if you have a power and an nth root, it's always power over root, right? Power over root. So I'm gonna turn this into a fractional exponent just because I think it's easier to see. So this thing right here, without me doing anything to it, this is x to the power over root. So this is x to the 2/3 power, okay? So if I want to get rid of the square root in the denominator, that means I need to get rid of the fact that this is a fraction, okay? I need to get rid of the fact that this is a fraction. So if I'm going to get rid of this fraction, I really am missing 1/3, right? Because if I have 2/3 and I put another third on there, that'll give me 3/3, which is just 1. But the only way that I can do that is by multiplying the top and the bottom by the same thing so that it doesn't change values. Well, when you're multiplying like bases, you add the exponents. So if I need to add a 1/3, then I need to multiply this by x to the 1/3 so that when I add those exponents, they cancel out. If I do that to the bottom, I have to also do that to the top. So the top is going to be 2x to the 1/3. And the bottom, x to the 2/3 times x to the 1/3, you add the exponents. 2/3 plus 1/3 is 1. So this is just x. And I would leave my answer like that. You could also convert this back into a root since we started with a root. So you could say, or you could say x to the 1/3 is really the first power over the third root. So this is 2 cube roots of x over x. So either of those two answers would be correct. Personally, I like this one because I would rather have a fractional exponent than a weird root, but that's kind of your preference. Looking at letter D, anytime you're taking a root of a fraction, you're taking that root of the top and of the bottom. So this thing, the fourth root of 1/3, is really the fourth root of 1 over the fourth root of 3, okay? Well, any root of 1 is always 1. So this guy is just 1. The fourth root of 3, I'm going to convert into a fractional exponent again. So this is now 1 over 3 to the power is 1, root is 4, so this is 3 to the 1/4. And I can't have a fractional exponent in the denominator, so I need to multiply by like base would be 3, and I need to make this into a whole number. So if I have a fourth, I need 3/4 to make it whole. So I'm going to multiply by 3 to the 3/4 on the top and on the bottom. This is our fancy version of 1 again, right? Because it's the same thing over the same thing. So on the top, that's now going to leave me 3 to the 3/4. And on the bottom, 1/4 plus 3/4 is 4/4, which is just 1. Okay? So this is 3 to the 3/4, so you can leave it like this. Or we could write it in terms of an actual radical again. So this would be the power over the root. So you could call this 3 to the 3rd, which is 27. So the fourth root of 27 over 3. So either of these two answers would be correct. It's, again, just personal preference and what they're asking you for on the multiple choice section maybe. This last guy is a little bit different because this one's actually got some subtraction. Anytime you've got addition or subtraction, you have to do something a little bit different. It's called rationalizing. It's called using the conjugate. So we've got to use the conjugate. So we're going to multiply by the conjugate, which hopefully is a word you've heard before. The conjugate of something is you keep whatever it is and change the sign in between. So the conjugate of 3 minus the square root of 2 is 3 plus the square root of 2. So we're going to do that on the top and on the bottom in order to rationalize. And you do that anytime there's addition or subtraction in the denominator with a root, okay? So you'll know pretty quickly, oh, I see it. I need to rationalize it using the conjugate. So look what happens if we multiply these together. 3 times 3 gives me 9. 3 times the square root of 2 gives me 3 square roots of 2. 3 times the negative square root of 2 gives me negative 3 square root of 2. And then the square root of 2 times the square root of 2 is the square root of 4. But the square root of 4 is actually 2, so it gives me this. Well, look what happens in the middle. I have the same term, so these cancel out. Okay? So when those cancel out, all I'm left with is 9 minus 2, so my denominator is now 7. Okay? So on the top, I've got 14 times 3 plus the square root of 2. My denominator is now 7. Well, I can divide 14 and 7. That's 2. So this is now 2 times 3 plus the square root of 2. Sorry, this should be a 3. 2 times 3 plus the square root of 2. So this is really 6 plus 2 square roots of 2. And that's rationalizing using a conjugate. So hopefully rationalizing is a technique that you already know how to apply, but if you didn't, hopefully this helps.